Hi all. So welcome to the last lecture on electrostatics in matter. So last lecture in the sense that it would be the last recorded lecture on electrostatics in matter, and hopefully we'll complete our both the modules, module 1 and module 2, with this topic, the Clausius Mossotti equation. Okay, and so hereafter, I think it would be better to discuss certain tutorials, so that obviously we'll do as a live session maybe in the next week. Okay, so we can discuss what is this Clausius-Mossotti equation. So Clausius-Mossotti equation is basically the relation between the microscopic and the macroscopic terms of electrostatics in matter. Okay, so we have know that the dielectric constant. So dielectric constant is one of the important constants to measure the electrical properties of the material. Dielectric constant we usually will represent by symbol epsilon r or capital K. Okay, and so this quantity is macroscopic quantity. Okay, so this quantity will define for a bunch of matter. Okay, now whereas we have another constant called polarizability. So polarizability is a microscopic quantity. So polarizability is represented by the alpha, and it is a microscopic quantity. So what I am going to do is I am going to derive a relationship between this dielectric constant and polarizability. That is, we can have a connection between a macroscopic and microscopic quantity. Okay, so microscopic in the sense that it is in the very small scale, and macroscopic in the sense that it is on the bigger scale. Okay. Now, the basic two things we have to remember is the definition of dipole moment and as well as the definition of polarization. So the dipole moment or induced dipole moment, usually we can identify by symbol alpha times E. So this E is the external electric field. We can represent as E else. Here alpha represent the polarizability and P represent the induced dipole moment. Similarly, we have also discussed what is the polarization. So the polarization of a material usually we can write as epsilon 0 chi times E. So this E is actually the total field inside the material. It should contains the applied field and as well as the induced field. So this electric field, that is what I have written here, is basically the applied field E else plus the induced field. Okay. Now, so usually we'll discuss this dipole moment in case of an atom. Okay, in case of an atom or a molecule, we can define P equal to alpha E. Suppose if you have some atom or a molecule like this, okay, central nucleus and surrounding electron. If you apply some field, what would happen is some dipole moment would produce here, because this positive nucleus will move towards right and electron will move towards left, and there will be some separation of the charges and thereby producing this dipole moment. And whereas the polarization will define usually in case of a bulk matter. Okay, so if you have a bulk matter which contains very large number of atoms or molecules, then here if you apply a field, what would happen is again some dipole moment would be induced here. Okay, and now due to this field, some dipole moment would be induced, so the atom would be its shape of the atom would change. Okay, so it will bulge towards one direction, and obviously there will be some dipole moment in the direction opposite the applied field, so that in turn produce some field. Okay, so we have two fields now. One is the applied field, we can represent by symbol E else, and the second one is the induced field, I can represent as E induced. So the total field inside this material would be E else plus E induced. So that the dipole moment per unit volume, this polarization. Okay, remember the polarization is nothing but dipole moment per unit volume, and this dipole moment per unit volume I can write epsilon 0 chi times E. Okay, now one of the problem we have shown that this induced electric field inside the material can be written as minus P by 3 epsilon 0. Okay, so I'm not going to derive it for the time being. Okay, so I'm going to use this result. So there is a relation between the induced electric field and the polarization produced. So the induced electric field I can write minus P by 3 epsilon 0. Okay, so with this uh, remarks, we can go for deriving the Clausius Mossotti equation. Okay, so the starting point is, as we already said, the total electric field inside a material I can write as uh, the the electric field applied, which is E else, plus the induced electric field. And how can I write my induced electric field? It is minus P by 3 epsilon 0. Minus P by 3 epsilon 0. Okay, so remember this capital P represents the polarization, and polarization is the dipole moment per unit volume. So suppose if N is the number of atoms or number of dipole moments per volume. Okay, so if capital N is the number of dipole moments per volume, then the polarization I can write capital N times small p. Okay, so therefore this becomes E else minus n times n by 3 epsilon 0 times small p. Now how can I write my small p? So small p can be written as alpha times E else. Okay, so therefore this become E else times 1 minus n alpha by 3 epsilon 0. Okay, so these are relation between the total field inside the material and the applied field. Okay, and here the alpha comes. Alpha is the polarizability. Okay, now again I am going to use this formula. This P equal to capital N times small p. Okay, so P I can write epsilon 0 chi times E, and where small p I can write N times small alpha times E else. Okay, so how can I write my E else here? So E else, if you use this result, then E else can be written as E by 1 minus n alpha by 3 epsilon 0. So this E cancels. So therefore we get epsilon 0 chi times 1 minus n alpha by 3 epsilon 0 becomes n alpha. Okay, so we can just modify it to reach the Clausius Mossotti equation. So some rearrangement may be required. Okay, so I can write this product of two times epsilon 0 chi minus epsilon 0 would cancel n chi alpha by 3 times n alpha. If you take this to the second term to the right side, so this become epsilon 0 chi n alpha 1 plus chi by 3. Okay, or okay, so or n alpha 3 plus chi by 3. Okay, so keep alpha on one side and take all other terms to the other side. So alpha I can write 3 epsilon 0 by n chi by chi plus 3. So this is your famous equation, the Clausius Mossotti equation. But you may wonder that this both alpha and chi are microscopic quantities. The chi is um, and alpha is the atomic polarizability and chi is susceptibility. The polarizability susceptibilities are the microscopic quantities. Now I can relate this one chi, the chi which is a microscopic quantity, I can connect that to a macroscopic quantity because the connection between the relation between the dielectric constant epsilon r, the dielectric constant epsilon r and chi is epsilon r. I can simply show that epsilon r is 1 plus chi, and it's also denoted by symbol capital K. And therefore alpha can be written as 3 epsilon 0 by n, chi become k minus 1, and this become k plus 2. Okay, so this gives a direct connection between a macroscopic quantity called k, the dielectric constant, and the microscopic quantity, the polarizability alpha. Okay, so this equation is called the famous Clausius Mossotti equation. Okay, so with this derivation, so it's a very simple derivation. Only thing we have taken the result of E induced here. Okay, so apart from that, there is no magic. Okay, so this we have not shown earlier. Okay, so hopefully we may show it in some tutorial session. That is how come the induced electric field can be taken as minus P by 3 epsilon 0. So apart from that, all other thing is well known to you. Okay, so I hopefully this gives a logical explanation for the Clausius Mossotti equation. Okay, so with this we have finished our all the discussion on the electrostatics in matter and obviously the electrodynamics one. And then only the remaining thing is we need certain tutorials on this topic and the doubt clearing sessions. So hopefully that we'll do in the next week as a live session. So thank you all. Keep watching.